Good morning, everyone. So today I'm going to provide a bit of an update on the surface geochemistry that Geoscience Australia has been doing. So to start with, I'm going to be talking about the Northern Australia Geochemical Survey, or NAGS for short, and then move into some of the preliminary machine learning results that we've gathered from this data. And then finally, I'm going to talk about the synthesis work that we've been doing on the regolith geochemistry of the North Australia Craton. So just as a bit of background, NAGS is part of Geoscience Australia's Exploring for the Future program, which is focusing in Northern Australia, as you can see on that map there. And that's about de-risking exploration for minerals, petroleum, and groundwater. So the main focus of NAGS was providing, one, environmental baseline data for the region, secondly, to provide data for agriculture, and finally, regional scale geochemical data to help provide information for mineral explorers as to rough areas that could be prospective. In this talk, I'm mainly going to focus on the use of mobile metal ion, or MMI, as a way of identifying areas of potential mineralization / distal footprints. So what is NAGS? As I mentioned, NAGS is a regional scale survey. It's low density and it's sampling the overbank sediments of catchment. So the image on the right there shows the location of the samples, so they're the blue dots, with each of their catchments in that light blue outline. So each of these samples, and there's 780 of them, represents a catchment of roughly 500 square kilometres. So the total area there is about roughly 2/3 the size of New South Wales. So it's definitely well and truly into the regional scale here. And the previous work that's been done at the large scale in this area was done by the National Geochemical Survey, which was almost an order of magnitude different in terms of density. So as you can see, we've really focused in on this area from the regional standpoint. So this video is just going to loop around. This is samples collected per day, coloured up on MMI copper. So being an overbank sediment survey, we sampled the overbank where available. However, as you get into Tennant Creek and west out into the desert, obviously there's not really an overbank for which you can sample. So in these areas, we sampled the topographic low or the swales of dunes where they were available. Unlike some of the previous surveys that we've undertaken, this only sampled the top material, so the top 10 centimetres, and this was done by digging a 1 by 1 metre pit, which was homogenised in order to get a somewhat representative sample. And then every 10th site, we collected a field duplicate at least 100 metres away. And this was to test the homogeneity of the sampling medium to try and determine if what we were sampling was truly representative, as a floodplain sediment should be fairly consistent over at least that scale. So in terms of analysis, we've used 3 different techniques here. MMI, as I mentioned, aquaregia digestion, and finally a total digestion. So total isn't 4-acid. In this case, it's dissolution of a fused glass disc using hydrofluoric and nitric acid in order to fully dissolve the sample, so we're getting a full representation of what's there. So we also analysed 2 different size fractions, a less than 2 millimetre and a less than 75 micron fraction, which underwent both the aquaregia and total. However, for the MMI, we only used the less than 2 mil. From there, we have quite a rigorous QA/QC process, and this is one to determine if the sample is suitable for mapping individually and whether we can actually trust the result we're seeing, and secondly, whether we can use the element in multivariate statistical techniques and whether we're confident that by putting it in there, we're going to get decent results and nothing spurious. So because we're using some multivariate statistical techniques, we actually use imputation, a k-nearest neighbour approach, in order to calculate values that are lower than the limit of detection. So when you do some of these techniques, such as principal component analysis, it doesn't handle missing values all too well. So you have to have some way of dealing with that. And I guess there's 3 main approaches you could take. You could either remove the sample or element that has the missing values, which isn't ideal. You can use the half limit of detection value, which I guess a lot of people would traditionally do. However, the main risk you run when you use half limit of detection is you are artificially creating a nice little population down below the detection limit, which some of these statistical techniques pull out, and you can see them very clearly. So we chose an imputation technique, which is shown to produce pretty good results for anything that has less than 50% missing values. In our case, we only accepted them if they had less than 30% lower than the detection. Following on from that, we performed a center log ratio transform, or CLR, and this is to open up the geochemical data. So geochemical data, as many of you might know, suffers from what's called the closure problem, in that as you start to perform statistical analysis on it, because it's multivariate, what you see is the potential for spurious results to creep into your data, and as well as hiding some things in the data that you might not otherwise see. Then from there, we perform principal component analysis as a quick approach of going through the data and finding out what the regional processes were in that area, as well as the correlation between the elements. And then finally, we've done some preliminary machine learning work, in this case on the MMI copper and the total fine fraction copper results. But why use MMI? As I'm sure many of you in exploration are familiar with, it's a very weak partial leach technique that hypothetically removes the adsorbed metal ions off the surfaces of clays and ferruginous regolith, and is potentially seen through cover. We do have a bit of a problem there in that it's been theorized that you can see up to 100 meters through cover, but you've got no way of knowing how deep you're seeing, or if over your area you're going to see variation in the depth. So one area could be seeing 100 meters, another area could be seeing 10 centimeters. So there is that unknown when you're looking at MMI data. There is also a very strong seasonal effect on things such as MMI or these other weak partial leaches, in that the wet and dry season has an almost order of magnitude difference between the results you'd see. So we collected all of our samples in the dry to try and mitigate this effect. So to get into some results now, this is the results of MMI copper. And when we overlay some of the mineral occurrences for copper, we can see we're starting to get a somewhat okay correlation between them. Mount Isa block comes up very strongly. This would be to be expected. There's a lot of copper in the region, and we're also seeing copper feeding in from the geology and going into the waterways, which would trend up towards the coast there. We do pick up what we're assuming to be red bank, just in the NT side there, as well as some of the mafic geology that we're seeing near there as well. As you can see, Tennant Creek doesn't come up at all, and that's consistent across a lot of the data. That appears primarily as a bismuth anomaly in this case. And then finally, you may notice we've got this trend running through the centre of the study area and then trending up into Queensland there. And this is a real problem. This is what we call the black soil plains. And it's really problematic, especially for MMI data, but for all the other digestions as well. So what we're seeing here is a really smectitic clay that's swelling and has a high adsorption potential for our metals. So as we go in on this regional scale, we've got this huge area with a large absorption potential versus areas that are more deserty or more sand-rich, which have a lower adsorption potential. So when we look at the data over a regional scale, what we're going to see is these black soils just producing high values and swamping out anything else that would potentially be there. So we have to find a way of getting around this. I'm not particularly hopeful that we'd ever see through the black soils. They're very difficult to look through. I know there's been some work that's tried to detect mineralization that's gone over underneath, and it drops off the second you change into the black soils any signal. So one such method that we're hoping to use is machine learning. But we can pick up the black soils in order to characterize where they are and where it's going to be an issue using principal component analysis. So they're particularly endowed on that positive end, so metals, silver, magnesium, copper, nickel, and then relatively depleted in the rare earth elements. So when we plot this up as a creek surface, we can see a very similar result to what we saw in copper. We see this trend down through the middle and then heading up into Queensland. And if I remove this creek surface here and overlay the bare earth satellite imagery, we can see where our main problem areas are and where we're correlating pretty well with the black soil plains. So between the first and second principal component, we can really identify these clay-rich areas and use them to try and reduce the effect on the overall data. To just step into the machine learning now, we use both the NAGS and the previously collected NGSA MMI data. So both surveys used the same sampling technique and methodology as well as analysis techniques. So we're somewhat confident that at least we're comparing like with like. And the reason we included the NGSA data is just to really increase the number of training points that was going into this area. Now we employed a random forest approach using our Uncover ML code, and this was done on the supercomputer over at the ANU. So we normally include about 70 different covariates that go into this, including magnetics, gravity, radiometrics, Landsat bands, climate features, and all of this gets fed in, and we use the data as our training. And what we're trying to produce here is a baseline result for the region. So what we're hoping the machine learning is producing is what you'd expect the environmental baseline for the entire region to be. What we're then looking at is where the misfit is, and in this case, where the strong positive misfit is, where we're seeing the results of machine learning significantly underfitting the results of the survey. So this is the results of the machine learning. So you can see the black soil plains coming up quite strongly there still. And when I overlay the points, I've got them colored up in 3 different ways. So the orange are our standard values. The white values are the somewhat anomalous on this upper end, and the blacks are the very high misfit values between the predicted and the actual. So again, just to overlay some mineral systems, we can see some correlations again coming in, but not much has changed between what we saw in the standard geochemistry and what we're getting from this. Just to really try and explain what these points are, so the orange values are those that sit pretty much the prediction would be here, and then if they sit anywhere within here, they get an orange dot. If they're higher than 1 standard deviation from the prediction, they get this white dot, and if they're greater than 2 standard deviations, then they get the black dot. But we are hoping this is one way of trying to determine where the highs within the highs are, and also the highs within the lows. So we are seeing some areas that are potentially interesting here, both in Queensland and in the Northern Territory. And now just to go into how data density really affects the machine learning results. So this is, again, the NAGS NGSA map, this time using the total digestion copper data. So as you can see, we've got a bit of a change in what we're seeing. We're still seeing this strong feeding effect from the Mount Isa geology into the waterways, trending up to the coast. But we're also seeing some geology coming up. So this band coming through here and up here, are particularly mafic rocks that are coming out quite strongly, and again volcanics coming out just in here. But if we increase the data density and sample more lithology types, so in this case I've included the more historic Headley, Siegel and Mammoth map sheet data that BMR collected back in the 1970s. So this adds about an extra 3,500 training points into the data set. And what we've really done here is refine the geological input into the model. So again, we still see features such as the black soil plains, but we've really refined where in the Mount Isa block is contributing to a lot of the signal that we're seeing in the waterways. So these particular geological units that are sitting here have quite a strong feeding effect, and they're contributing quite significantly, one could infer based on this, into what we're seeing in the waterways. Again, the black soil plains, and then we can see the feed-in that enters in as we get into Queensland. And finally, the geology that we're starting to pull out. So as we start to include more elements, we can pull out different features. So this area is particularly nice just due to the pure data density, but we start to be able to see different phases in the granite that's up there if we start to use different elements. We can pull out the mafic ultramafics. So as I said, this is preliminary work, but as we start including more elements, we're hoping we'll be able to pull out a lot more information from this data. Now just to finish off, I'm going to talk about the synthesis work that we've been doing on the North Australia Craton. So all up, we've got about 16,500 data points from historically collected state, territory, and federal geochemical surveys. I've kept it to just these ones, purely based on the fact that it's easy to access the material. The reports are readily available, including information on the standards that were analysed. And from there, we're hoping to be able to produce a seamless map of the North Australia Craton's geochemistry. In this case, we're only using the fine fraction total digestion, because this is the most consistent component across the entire region. So I've just got a very quick video to show the sampling density, because it's quite hard on a map like this to indicate. Where's my mouse gone? So we've got the GSWA samples, which were done in a gridded fashion. They pretty much sampled whatever was underfoot, unless it was a rock. So we have quite a wide range of regolith types coming in there. This is the historic Headley, Seagull and Mammoth Mines data sets that I used in the machine learning earlier. And then finally we get into Queensland, which has an absolute mammoth amount of sample sites. So this is the old BMR, AGSO, Georgetown and Cape York study. We also in this area have the recently acquired GSQ regolith samples, which followed a similar methodology to the NGSA, as well as the NGSA samples that cover the entire area. So we've really got a decent data coverage, especially in the NT in Queensland. There's a few gaps as we get into WA. Now in terms of a process, what we've done is we've analysed as a central batch a group of standards and some of these historical samples in order to provide a single point to which to level. So this is done in two processes, whether the standards are available or whether we have to use the historical data. So in terms of this, we plot up the results of, in this case, TIL1 and check the normality of the distribution. If we're assuming normality, then we use a Welch's t-test. If not, we use a Wilcoxon sign rank test. And this is really to test if the populations are the same. It's the same material, it's the certified reference material, we should be seeing the same results. However, in reality, it's never that easy. So as the image on the top there, that's calcium between the NGSA in this case and the central batch that we ran. So we can see the results if we look at just the numbers, 2.67 versus 2.78%, pretty similar, about 4% difference. I bet a lot of people when looking at geochemistry wouldn't bat an eyelid of 4% difference between the results. It's not a lot. However, when we actually look at the density plots for the results, we can see they're very distinct populations that are sitting in there. And then for the legacy samples, which represents that bottom plot there, so this is data from the Headley Seagull mammoth sheet from the 1970s versus the reanalysis. So what we're seeing is a pretty good correlation between the two. And we're basically correcting this just using a rearrangement of the simple straight line equation. So just re-equilibrating down to that y equals x. But you might be thinking, why is this an issue? Things like 4% are pretty meaningless. So to test if this was going to have any sort of effect, we looked at the old Southern Thompson geochemistry survey that was undertaken. So this is data that was collected in 2006, 2007 as part of CRC Leam down in New South Wales, and then was continued as a Ulo-Tumpine extension into Queensland. Now this followed the same methodology, same analysis techniques. The only difference was the lab that analysed them changed in this period. And as we can see on the top plot there, this is principal component 1 versus principal component 2. There's a very distinct difference between the two. This is, the main driver of the data is this first principal component, and we can easily separate them. I wouldn't even need to call them up. You'd be able to draw the line and tell me where the two surveys were. So that's quite concerning. These were surveys that were done using a large number of standards, duplicates, repeats. Everything was done by the book. All the values were more than acceptable, but as we plot them up, we can see there's definitely issues here. It also produces a good data set in which we can test the leveling methodology, in that we can use both the TIL1s that were analysed as part of the Ulo-Tumpine, and we also reanalyze some of the old CRC Leam samples as well. So as you can see on the bottom plot there, we've significantly fixed this difference. I can no longer draw a straight line between the two surveys, so we're really, at least in these first two principal components, reducing the effect of any mismatch in terms of lab calibration curves. We do see some difference, especially on that y-axis, but this is potentially now where we're seeing some actual geological meaning coming into it. There is a difference between the New South Wales and the Queensland side. We're getting into more granitic territory as we move up into Queensland with actual outcrop. So this is potentially where this difference is, but at least we can be a bit more confident in the data that we're looking at is actually somewhat leveled together and can be used for more multivariate statistical analysis. So just as a quick progress report, anything in green has been leveled. All that's left is a few GSWA data points and the recently acquired GSQ samples. So they're currently in the Geoscience Australia lab as part of a collaboration. So we're rerunning them with a large batch of standards so we can level them in as well. And then finally produce this seamless map for the area, which should hopefully produce some interesting results. So just as a quick conclusion, we see a somewhat okay correlation, especially in copper, with the known mineral systems. There is potential to indicate new prospective regions. The machine learning at least allows us to produce high resolution background images for the region to try and get the patterns that are happening within there. And there's also potential to try and use this machine learning as a way of determining prospective regions in this regional data. That's all I have today. Thank you.